Okay, so good evening, everyone. Welcome to the 10th live session for the course Concrete Technology offered by NPTEL. I am Harshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the entire course duration. So for those who have joined the session for the first time, these are weekly interactive sessions that are held every Tuesday from 6 p.m. to 8 p.m. During the session, we interact either by answering to the questions that I will ask in the chat box, by posting your questions in the chat box, or by raising and unmuting and asking your queries. Apart from the live session, you can always use the discussion forum of the course for clarifying your doubts. And attending these sessions regularly will help you to answer the graded assignments easily and will help you to further understand complex topics holistically. So, in today's session, we'll first have a quick revisit to the last live session that was for a week 9 content, and then we will look into the things that was covered in the week 10 of the course. So, in the week 10 content that we'll discuss today, we will continue our discussion on the properties of concrete, where today we'll start with the durability properties of concrete. So for this, the session is divided into following sections. First, we'll talk about basic overview of durability and service life. Then I will touch a little bit upon retrofitting, repair, and rehabilitation of concrete. Then we'll talk about how durability is affected due to different degradation mechanisms of concrete. In degradation mechanism, specifically, we'll talk about sulphate attack, acid attack, alkali aggregate reaction, and freeze thaw attack, or what was shown in the NPTEL session as frost attack. Then we'll talk in brief about corrosion, just overview of corrosion, and then the means by which corrosion in concrete occurs, that is due to carbonation and chlorides. Finally, we'll conclude the discussion and I will try to address any other queries post discussion. So in between, we will have some objective question and maybe a couple of numerical questions also. So in total, there will be around 17 questions that will help you to, that will challenge your understanding on the concept. So last week we concluded the ninth week of the course, where we continued our discussion on mechanical properties of concrete by discussing about modulus of elasticity of concrete. In modulus of elasticity, we discuss what is MOE, why concrete shows non-linear inelastic behavior in stress-strain relationship. We talked about different MOEs of concrete, different ways to measure MOE, that is using static method and dynamic method, different types of MOE based on the direction of deformation, and finally how concrete properties can affect the MOE value. Then we talked about fatigue in concrete, why fatigue occurs, and we talked about two types of fatigue deformation, that is creep fatigue and cyclic loading fatigue. We discussed about bond strength in reinforced concrete, how concrete and reinforcement property affects the bond strength. There we saw three cases, and how bond strength is determined using pull-out testing. Then we discussed about creep in concrete. What is creep? Basically, it is a deformation under sustained loading condition. We understood the same using a stress strain relationship that you can see on the slide, and we saw how creep, recovery, or relaxation occurs. We talked about how concrete properties affect creep in concrete and then moved into the prediction of creep from present or past data. First, using ACI model, where creep coefficient is determined after a time t in loading, where we have applied a load at a time t naught, and based on ultimate creep coefficient, which takes into account the environmental and material properties, we can determine the creep coefficient after a time t under loading. For the same prediction, we saw British standard method also, where there is a standard correlation curve which is present for estimating the creep coefficient based on the age of loading, the relative humidity of the surrounding, and the volume to surface area ratio of the concrete structure. After prediction, we talked about how creep is measured in laboratory based on ASTM C152 method, where we have concrete cylinders which are subjected to sustained loading condition, and deformation is determined after different time interval using deflectometer. At last, in creep, we talked about once concrete is under creep deformation, what are the different stages of creep deformation. Like there is primary stage, secondary stage, tertiary stage, and finally there is fracture. And we saw how when concrete is under some multiple loading condition, failure can be determined using Minner's rule. After creep, we talked about shrinkage, where we first discussed different types of shrinkages, mainly plastic shrinkage, which occurs in fresh state, drying shrinkage in hardened state, autogeneous or chemical shrinkage due to cement hydration, and carbonation shrinkage due to CO2 ingress. Similar to creep, using ACI 219 method, we saw how shrinkage can be predicted based on ultimate shrinkage coefficient, which takes into account the environmental and material properties. And then using BS method, where volume to surface area ratio and relative humidity is used to predict the shrinkage after 6 months and ultimate shrinkage. And finally, we discussed about measurement of shrinkage, with the first being length comparator for determining drying shrinkage based on IES 49459, autogeneous shrinkage, which can be determined based on ESTM C1608, and ring constraint shrinkage test, which is based on ASTM C1581 method. Okay, so this is where we ended the last session. Now, till date, we have talked about individual components of concrete, mixture designing, and mechanical properties of concrete. Now, the final segment of concrete discussion is the durability of concrete. When we talk about modern day concrete applications which is having adequate in which having adequate strength is not enough for concrete design. Okay, we they and why this is so, like, why strength is not the sufficient parameter anymore for design of concrete? Because there has been raising cases of premature failure of concrete due to degradation. So that's why durability of concrete has become an important factor, and as important as the strength of concrete. Now, what is the technical definition of durability? Like, what do we mean by durability? So if we see the definition of durability that is given by American Concrete Institute, so durability of concrete is defined as the ability to resist weathering action, chemical attack, abrasion, or any other form of process of deteriorations. Okay, so now, this is what durability mean. Now, when do we say that a material is durable? Like, we know durability is a property to resist external actions, but how can we say that our concrete is durable? So for this, if we see an IS 456 design, or 456 definition, it says that a durable concrete is defined as one which performs satisfactorily under a expected exposure condition for a specified service life or lifetime of a structure. Now see, here both the definitions, both are defining the same thing but from a different angle. The first definition by ACI talks about what durability means in terms of resistance to weathering action. And the second definition by IS code says about the response of concrete to its weathering action as a term to define the durability. Now, if we see in the second definition, there is a word that is used here, which is service life. Okay, so it's not like I have prepared a concrete and it will last for lifetime. No, concrete will naturally degrade over time. Okay, and that natural degradation is what we consider while designing the concrete in terms of service life. Okay, so there is always a natural degradation that will happen in concrete due to the exposure environment, and that is what we consider initially while designing the concrete. Okay. Now, so service life of concrete, it can be defined as the assumed period for which a structure or a part of it is to be used for its intended purpose with anticipated maintenance, but without major repair when necessary. Okay. Now, what this definition mean to say, suppose I have a structure which is I have designed for 100 years. Okay, so my structure will be said to have a service life of 100 year if it is able to perform its function, the function for which the structure was built properly, with some anticipated maintenance like minimum maintenance, but not any major repair requirement. So suppose I have a building which is designed for to serve as a laboratory purpose. Now instead of laboratory I'm using as a teaching hub. So that is the change in the functionality. So that means the service life has ended. Service life is only defined when the functionality of that building is also the same and it is serving its functionality properly. If I'm decreasing the functionality of my building, I'm affecting the then also I'm going out of the service life, or the predefined value that I have taken. Okay, so if there is degradation apart from this pre-planned one, then the service life of concrete will be lower. Okay, now on this slide you can see a basic flow chart that describe both definition by ACI and by IS code that we have talked about. So durability is a function of both concrete system as well as the aggressiveness of the environment. Okay, so we have both concrete system and the aggressiveness of the environment. Okay. In concrete system, it is governed by the quality of concrete, which is again dependent upon the both material that is used in concreting, like binder type, binder composition, binder content, aggregates, admixture, and the mixture design. While the process post mixture design till setting of concrete, which in a specific structural element. Okay, so that process also can affect the durability of my concrete system, like mixing, transporting, compaction, curing, temperature, and workmanship. Okay, so this is the concrete system effect on durability. And the aggressiveness of the environment decides the degradation or deterioration of concrete. Okay, which can be either physical due to abrasion, erosion, cavitation, or freeze thaw, or it can be chemical due to dissolution, leaching, expansion, and alteration. Okay, so I have both quality of concrete as well as the degradation or deterioration of concrete, which both will affect the durability of concrete. So this figure just simply explains about deterioration, how deterioration is affecting the service life or performance of concrete. So the gray dotted line that you can see here, this shows how the performance of concrete will degrade naturally. So initially my performance of concrete is at this point. Now naturally this will degrade until I will reach a critical performance limit, which will mark the end of my service life. However, if there is extra unplanned deterioration that is occurring in concrete, so what will happen? My concrete performance will degrade at a faster rate. So, this critical performance line that I have marked, I will breach that line much earlier than the anticipated service life. So, this was my anticipated service life, and this is the service life that I am getting due to aggressive environment or increased deterioration of concrete. So this gap in between defines the loss of structure life due to deterioration. Okay. Now to counter this degradation comes the role of repair, retrofitting, and rehabilitation. Okay. So at timely interval during the degrading performance, some measures are taken to improve or restore the expected performance of the concrete. So you can see here in the green line, so my concrete was degrading, then some repair maintenance was applied, so my concrete's performance was increased again. Then again it starts to degrade, then again the performance was enhanced after some time, and in this way I am able to reach the expected service life of structure with in certain maintenance in between. So this is how service life is defined. Like the definition that we saw, this functionality is the same, but there is some anticipated maintenance in between by which my structure is able to serve its intended lifetime period. Okay, so this regular maintenance, it leads to increment in the service life. Now this is just an additional point I want to discuss, but often it is like very important to have clarity of, and that is what is the difference between these three R's, that is repair, rehabilitation, and retrofitting. Like what we mean by these three terms. Okay, so when it comes to existing building or structures, there are three main strategies that are used: repair, retrofitting, and rehabilitation. So what do I mean by repair? Repair means to restore a structure to its original condition. So initially whatever condition was there, I need to restore the structure to the same condition. That is known as repair. And how it is done? It is done by replacing the damaged element, restoring the lost feature, and repairing the system which are in functioning as intended. So this is what is done in repair. It is cost effective and quick, but it doesn't address any age related issues. So due to aging, if some degradation is happening in the material, that won't be addressed. It will just replace the damaged element or restore some lost feature that is there in the system. Now second is retrofitting. So retrofitting, the aim of doing retrofitting is to adapt a structure to a new use. So suppose I am changing the functionality of my structure. I am increasing, suppose I my structure was designed to take 100 kilonewton load, but now I want my structure to take 150 kilonewton load. So for that, retrofitting is done, strength enhancement is done on the structure, so it helps the structure to adapt to a new use. And how it is done? By modifying the existing building to suit a different purpose. Like for this we have jacketing or FRP wrapping. So all these techniques comes under retrofitting, which helps to increase the strength of the structure. Now what is the advantage here? We are increasing the functionality of the structure, but at the same time it can be expensive and time consuming. And finally there is rehabilitation. So it the role of rehabilitation is to bring a building up to a certain standard by adding more features or systems in the building. So we are making a building come up to a standard criteria of use, that is known as rehabilitation. And the process is to modify the structure for safety, comfort, and efficiency. So for safety, comfort, and efficiency enhancement, rehabilitation is done. Its advantage is that it enhances the safety, comfort, and efficiency, but it is time consuming and can be expensive sometimes. So whether to choose repair or retrofitting or rehabilitation, it depends upon the degradation level that has happened in the structure and the functionality of the structure. Okay. So repair and retrofitting we can understand from these two figures also. So if we keep deterioration and performance on y-axis, so you can see on the left side there is deterioration, on the right side there is performance. Okay, and we keep time on the x-axis. So what repair does? It increases the durability of the structure. You can see here it is increasing the durability of the structure, but it does not affect the strength or any change in functionality in the structure. So by increasing the durability, what it is doing, it is slowing down the rate of deterioration. So suppose this is the performance, critical performance, where my structure service life will end. So I have increased the durability of my structure, so this point I will reach later on. So I will have I will have more service life compared to what I was going to have. Okay, so this is repair. And what does retrofitting do? So in retrofitting, instead of causing any change in the um, in the it, like in retrofitting we are increasing the strength. Okay, so we are not changing the rate at which degradation is occurring, but we are enhancing the performance of my structure, or we can say strength of the structure, which will in turn delay the service life end, and it will increase the durability of my concrete. Okay, so it increases the level of performance of concrete. As you can see here, instead of delaying the slowing down the rate of deterioration, we have increased the performance of concrete and delayed the end of service life. Okay, so this is about retrofitting and repair. Now, this course is about talking about concrete degradation. So, this retrofitting repair part I will drop here only. But if anyone is interested in this, like to know more about repair and retrofitting, they can visit my YouTube channel where I've presented a course. Last year on repair and retrofitting of concrete infrastructure, that was also part of NPTEL. Generally in the this January window only that course runs. So if you want to learn, you can go through those session recordings that will help you to learn more about this topic. Okay, so now we will talk about degradation in concrete, like what are the different ways in which concrete can degrade. Okay, so it can happen in several ways. There can be mechanical degradation, which is due to abrasion, erosion, impact, or explosion. There is physical degradation, which is due to freeze thaw, creep, shrinkage, and fire, out of which we have seen two. There is structural degradation due to overloading, settlement, and fatigue. Fatigue, we have also seen. Settlement is the differential settlement of soil, and overloading is like we have designed a structure for a certain limit and we are loading it more than that limit, so that becomes overloading degradation. Then there is chemical degradation, which can be due to alkali aggregate reaction, acid attack, and sulfate attack. There is biological degradation due to fouling and biogenic attack. And then there is corrosion of embedded reinforcement. Okay, so for today, we will be discussing about this chemical degradation and corrosion. Now, both of these category, corrosion and chemical degradation, they are highly dependent upon the presence of moisture as a key agent in the contributing the ingress of chemicals and other ions which are responsible for degradation. Okay, so less permeable is my concrete, better will be my resistance to the degradation processes. Okay, so you can see here all chemical reactions in presence, all chemical reaction involves the presence of moisture, and they often involve ingress of aggressive chemicals and moisture. Okay, so moisture is the key thing when we talk about durability of concrete. So, based on this initial discussion about durability, service life, and repair retrofitting, just try to answer these three questions. And in between, in the meantime, if anyone has any doubt regarding this initial introduction of what we have discussed today, just let me know in the chat box, or you can unmute and speak also. Okay, any doubts? No. Just try to answer the first question. Which of the following statement is true regarding the durability of concrete? So, what will be the answer? Okay, can anyone else also try? Okay, so for the first question, the correct answer will be C. Okay, how? So, SCMs like fly ash, silica fume, and slag, what they do, they reduce the porosity or pore connectivity in concrete. So, if my porosity of concrete or pore connectivity in concrete will reduce, so what will happen? All these aggressive ions, which are responsible for chemical attack and corrosion, they won't be able to go deep inside concrete, or they won't be able to move through the concrete. And in this way, it will improve the resistance of my concrete against durability affecting processes. Now B here will be incorrect. Why? Because if I will have higher water to cement ratio, though it will improve my fresh state property, like it will improve the ease with which I can work with the concrete, but if I have a higher W by C ratio, my strength of concrete will be lower and there will be more porosity in my concrete. If there is more porosity in concrete and more moisture in concrete, then the aggressive ions from surrounding which are responsible for causing durability issues in concrete, that will enhance the, like, that will degrade my concrete more, because they have found a medium to move through concrete. Okay, so I want my concrete to be as much impermeable as possible, like it should have the lowest porosity as possible so that the ions can't move through concrete. Okay, so that's why answer can be C. Answer will be C. Okay. Question number two. Which factor has the greatest impact on the long-term service life of RC structure? So what will be the answer? Okay, for question number two, I've received some answer as B or D. Okay, multiple answers I've seen. Okay, so for two, the correct answer will be B. Okay. Someone mentioned D also, avoiding reinforcement to risk avoid corrosion risk. Okay, that is true, but see, concrete can't take tensile load. Okay, and in practical application, there will be tensile load that also will be needed to resist for concrete to resist. So that's why we are using reinforcement. Though reinforcement has risk of corrosion, but that cover concrete, if we will make the cover concrete very dense and impermeable, then we can avoid that risk of reinforcement, or we can delay that risk of reinforcement as much as possible. So reinforcement is a very crucial part of my structure for in terms of practical application. So for this question, the correct answer is B, because concrete durability, it is primarily controlled by the ability of my concrete to resist aggressive agents like water, chlorides, and sulfates. Okay, so if my exposure condition has a lot of aggressive agents, then it will risk my long-term service life. And if my concrete is more permeable, then it will have a higher risk on the service life. So these two parameters, controlling these two parameters, is the have will have the greatest impact on the long-term service life. Question number three: in retrofitting of concrete structure, FRP wraps are primarily used to. So, what is why we do FRP wrapping on concrete while during retrofitting? Can anyone guess the answer? So, for third, I have received multiple answers. Okay, mostly people are saying B. Any other opinion? Not shrinkage. Shrinkage is a like concrete property, like it will happen in fresh state, hardened state, and that is mainly due to the cement paste or the composition of my cement paste. So FRP wrapping is something that we are applying externally. Yes, shrinkage can like reduce the rate at which water is evaporating. That can be one case, but in retrofitting, we have specially talked a couple of slides ago. Retrofitting, why we do retrofitting? To enhance the performance of my concrete, like increasing the strength of the concrete. Okay, so that's why the correct answer will be B. Okay, improve ductility and flexural strength. So what is FRP wrap? So if we have a concrete column, suppose we have a concrete column, so there is FRP materials which are externally wrapped on that concrete column. Now what that wrapping does, it provides some confinement to my column, and that confinement helps my concrete to take more load than it was able to take. So suppose my column was able to take 100 kilonewton of load. Now with proper FRP wrapping, I can make my concrete column to take up to 120, 130 kilonewton of load. Okay, and it may can be also similarly for other application, like for improving the flexural performance or shear performance or axial performance. I can use FRP to improve the ductility or strength of concrete. Okay, depending upon my need. Okay, so retrofitting, main function of retrofitting is enhancing the performance or strength of my structure. Okay, so this was about basics of durability, service life, and how service life can be enhanced. Now we'll talk about chemical attacks. Like couple of slides ago, we have seen different degradation methods, and now we'll go specifically into the chemical attacks that is responsible for degradation of concrete. So in chemical attack, let's start with the sulfate attack in concrete. Okay, so sulfate attack is basically a reaction between sulfate ions and hydrated cement products. Okay, now there can be two forms of sulfate attack. There is external sulfate attack and there is internal sulfate attack. So sulfate attack, sulfate ion ingress through concrete from groundwater or seawater or due to bacterial actions in sewer. Okay, so these three can be the source of sulfate ions from surrounding. Okay, an internal sulfate attack occurs when there is a late release of sulfate within concrete. Okay, and in this case, what happens? There is a formation of ettringite which occurs after the concrete has hardened, and this process known as delayed ettringite formation. So, how this affects concrete, we'll see couple of slides later. But for now, you can remember the definition. External is due to sulfates coming from surrounding, and internal sulfate attack is due to the late release of sulfate ions in concrete. Now, what is the end result of this sulfate attack? So it causes softening and loss of integrity of concrete. Okay, and due to this, my concrete deteriorates at a faster rate than expected. So to limit this sulfate degradation, what IS code says that the total water soluble sulfate content in a concrete mix, which is expressed as SO3, should not be more than 4% by the mass of cement. Okay, and aggregates should not contain more than 5.5% sulfates as SO3. Okay, so that's why there are limits that are imposed on cement and aggregates. So that's why we do initial chemical characterization of materials so that we can know if there is not much or not over the limit of these aggressive ions which are present in our material. Now, how sulfate attack occurs? So basically, each individual hydration product can give rise to a new compound because of sulfate attack. So this is a fact. Okay. Now, the primary products that result from sulfate attack is the gypsum and ettringite. So we have three equations here how sulfate ions are causing degradation of concrete. In the first equation, we have calcium hydroxide, which reacts with sulfate to form gypsum. Okay, so CH with the reacts with sulfate to form gypsum. So in this way, pH of my concrete is decreasing. Okay, then the second reaction, and in the third reaction, there is ettringite formation that is happening. Okay, when sulfate reacts with either monosulfates or calcium aluminates. Okay, so we have ettringite formation, and when we have seen earlier, like in week 1 or week 2 session, that monosulfate or ettringite formation leads to increase in volume, while if ettringite is forming and this is forming in hardened state, then it will cause degradation in concrete due to that increase in volume. Now, what happens this when this reaction happens, due the conversion of monosulfate to ettringite, this swelling also that occurs due to consumption of water. So you can see here there is a lot of water that is consumed in these reaction. Okay, and due to this swelling, it has a because of which there is high surface area of ettringite which can give rise to cracking and disintegration in concrete. Okay, so this swelling, if it occurs in hardened concrete state, I have a very compact system. There is not much free spaces that are available. But if such reaction will occur in the hardened concrete state where ettringite will demand for more volume or more space due to its high surface area, that can result in tensile cracking inside my concrete, and which can lead to degradation of my concrete. Okay, now, these are not just three reactions where sulfate ions can contribute. Other reactions can result in progressive loss of stability due to sulfate ion attack is on the calcium silicate hydrate. Okay, so what happens? This calcium silicate hydrate, sulfate ions causes damaging effect on CSH gel only due to action of magnesium sulfate. So what happens if there is magnesium sulfate in concrete, it can react with CSH to form gypsum and MSH, which is known as serpentine, and it has a poorly crystalline material. So, since my CSH is getting disturbed, which is my main strength bearing phase of my concrete, and if it is getting disoriented or consumed in any other form, then my concrete will start to degrade because it will start to lose its strength. Okay, because CSH is my main strength bearing phase of the concrete. Now, this is something you can relate from our discussion in week 1 or week 2 also. So, you see here in the figure, there are three types of cement: type 1, type 2, and type 5. So, at a particular W by C ratio, suppose zero point 0.6, that swelling effect that we have recently talked will be directly proportional to the amount of ettringite formation, and that ettringite formation will be dependent upon the presence of sulfate and primarily on the amount of aluminates phases that are there in the cement. So that's why type 5 cement has the minimum expansion due to sulfate attack, while type 1 cement has the maximum expansion due to sulfate attack because it has more C3 content, while type 5 content has the least C3 content. So if 3 C3 content is low, we know that monosulfate formation will also be low, so that ettringite formation, risk of ettringite formation due to sulfate attack will be reduced. Okay. Now, especially in case of internal sulfate attack that we saw in the definition earlier, there is a thing that is known as delayed ettringite formation, which simply means that the formation of ettringite in concrete is happening at later stages after the initial curing period. Okay, so that ettringite formation is getting delayed. Now, when such condition will arise, so it occurs in concrete that experienced a elevated early temperature. So if you suppose initially during curing phase, or like initial 24 hours or initial curing phase, if the temperature of my concrete is elevated above 70 degrees Celsius during curing, then it will prevent the formation of normal ettringite. So initially there won't be any formation of ettringite if there will be high temperature curing. Now, in such condition of concrete, what happens? Sulfate concentration in pore solution is high for an unusually long period of time in hardened concrete, since it is not consumed to form any monosulfate or ettringite. And then at later stages, once the concrete has hardened and the temperature has become lower than 70 degree, the sulfate ions, they react with calcium and aluminate containing phases to form ettringite. Now, this formation of ettringite in hardened concrete in the presence of moisture leads to generation of expansive pressures and cracking in concrete. And this process of for delaying the formation of ettringite in concrete is known as delayed or secondary or late ettringite formation. Okay, so under such high temperature curing condition, initially ettringite is not forming, but in the hardened state, ettringite is forming. And since ettringite occupy more volume than expected, they can cause cracking in concrete, and this can give rise to degradation of my concrete. Now, the effect of sulfate attack we can see here also in the first image, where you can see it is a microscopic image where, okay, where is my mouse? Where I have a cement aggregate interface, and where you can see there is this gap where ettringite lining has resulted in 2.8% expansion. So this will lead to cracking in concrete because it is occupying unexpectedly high space in my concrete structure. While in the second image, it shows a typical case of some submerged column which is experiencing bulging due to expansion as a result of sulfate attack from seawater. Okay, now how to prevent sulfate attack? There can be different ways, or how to delay sulfate attack. We can use sulfate resisting cement which has low C3 content. We can use SCMs which has low CH content. We can make concrete impermeable, or we can use a low water to cement ratio which will reduce the porosity of my concrete. So making concrete impermeable or reducing the CH content or reducing the C3 content, they all can have a positive effect on delaying the sulfate attack or reducing the risk of surface sulfate attack. Now, after sulfate attack, we have acid attack in concrete. So there can be variety of acid which can degrade concrete, like there is nitric acid, acetic acid, hydrochloric acid, and carbonic acid. But the majority of degradation that happens due to attack in concrete is due to sulfuric acid. Okay, which is commonly observed in sewers, where lot of sulfide gases exist owing to the large degree of microbial action that is there in the sewage lines. Okay, so in sewers it is rich in sulfide ions. Okay, and due to the sulfide ions, when they are released in the open space in the pipeline, under this in the presence of oxygen, they form sulfuric acid. okay, which creates an acidic environment in the concrete lining, the pipe lining which is present around the sewer lines. And this acid, it degrades the chemical phases, cement phases in concrete like CSH and ettringite. They become highly unstable and they start to degrade. Once they will degrade, concrete will lose its strength, its binding ability, and the concrete will collapse. Okay, so you can see here, gypsum formation occurs when sulfuric acid reacts with CH. The loss in integrity and softening of the structure occurs as a result of gypsum formation and destabilization of CSH at low pH. Okay, so this is how my acid attack is leading to degradation in concrete. Okay, so you can see here in the two images also. In the first image, here there won't be any sulfate attack because this is anaerobic condition, there is no oxygen inside my water. However, when hydrogen sulfide gas is released by the sewage water in the presence of oxygen and biogenic condition, this H2S gets converted into H2SO4, and this H2SO4 can attack the concrete linings here, or you can see here in the pipe. Okay, so these concrete linings, they are getting attacked by H2SO4, and this leads to degradation of the concrete. Okay, so here in the first image, one can see the example of a sewage pipeline where concrete walls have experienced severe degradation, which is visible from like peeled off zones here and here. Okay, and some exposed rebar also, which was being able to which was visually available. Okay, so this is how acid attack can affect the tunnel wall. Okay, in sewage lines. Okay, how to prevent acid attack? We can use some preventive protective coating like as surface treatment like epoxy coating or coal tar, so that we can this nullify the reaction of H2SO4 with the concrete. We can use some antibacterial cement which can nullify this reaction, or we can make concrete impermeable. So if we'll make concrete impermeable, what will happen? This hydrogen sulfide, it won't be able to go inside concrete, and if it's not able to go inside concrete, then it won't be able to disintegrate the CSH or CH inside concrete. Okay. Any doubt in these two topics, sulfate attack and acid attack? Okay, I see no doubts here, so I will continue. Now, after acid attack comes alkali aggregate reaction. So, what is alkali aggregate reaction? So, it is a reaction between alkalis and the certain specific types of cement. Okay, so here alkali here comes from the uh, different individual components of concrete like cement, chemical admixture, mineral admixture, or impurities in aggregate and water. So that they will be the source of alkali, and aggregates come from, and this the specific reagents like silicon carbonate which are responsible for alkali aggregate reaction, they come from the aggregate, or which can say amorphous aggregate. So generally we assume that aggregate are inert in nature. However, if there is amorphous impurities in aggregate in the form of silicon carbonate, they can react with alkali to show alkali aggregate reaction. Now, if we simply write this reaction, what is happening in this reaction? So we have alkali ions from my cement or other phases inside concrete, and we have reactive silicon carbonates that are present in the aggregates. So these two agents, ions, in the presence of moisture, they form alkali silica gel or alkali carbonate gel, we can say. Okay, so generally we represent as a ASR, alkali silica reaction gel. Okay, now this gel is expansive in nature. Okay, so if it is expansive in nature, it will generate tensile stresses inside concrete. And if those stresses, if they are more than the tensile strength of concrete, they will cause the cracking in concrete. Okay, so alkalis in the presence of reactive silica, it forms alkali silica reaction gel, which is expansive in nature and which leads to cracking in concrete. Now, how this alkali silica reaction occurs? Okay, so for this, I have this flow chart kind of diagram. So first, we have amorphous silica in aggregates, and during cement hydration, alkalis have been released in the pore solution. So this is step one: release of alkali in the pore solution in the vicinity of aggregates which have amorphous silica. Now, in the presence of alkaline medium, the silica and aggregate they break down due to hydrolysis to form silanol groups. Okay, so you can see here I have silicates in aggregates. Okay, due to the high alkaline environment, they react with water to break down into SiOH, SiOH compounds. Now, this silanol groups they further break down in the presence of alkali ions into SiO negative ions. Okay, so this reactive silica that will again break down into SiO negative ion in the presence of alkali ions or high pH. Okay, now this released SiO negative ions from aggregate, they react with the alkali cations that are present in the pore solutions like Na plus K plus in the presence of water to form gel around the aggregate. So you can see here this gel formation has occurred over the top of my aggregate. Okay, so this released SiO negative molecule they attract the alkali cations from the pore solution, forming a gel around the aggregate. Now, this gel is known as alkali silica gel, which starts to swell due to imbibition of water, which again results in cracking of concrete. So this gel has the capability to absorb water, and if it will absorb water, it will start to swell up. And since it is expansive in nature, and my concrete has very restrained pore structure, this expansive nature will generate lead rights to cracking in concrete, which will cause the degradation in concrete. So this is how alkali silica reaction happens. So initially there is release of alkali ions. The reactive silica in concrete in the presence of alkali ions they form silanol groups, SiOH groups. This SiOH groups further breaks down in the presence of alkali environment into SiO negative ions, and these negative ions they react with the cations which are present in the pore solution to form a gel around the aggregates which has ability to absorb water and expand. Okay, now, the degradation due to this alkali silica reaction in concrete, they generally appear in terms of map cracking that you can see in the first two images. Here and here you can see how map cracking has occurred all over the concrete surface, and this can be due to alkali silica reaction. While in the third image you can see this gel formation that is happening at the uh, aggregate surface, cement aggregate interface due to alkali silica reaction if my aggregate is amorphous in nature. So similar to alkali silica reaction, there is alkali carbonate reaction where the alkali hydroxides which are present in the cement or in the pore solution, it reacts with the magnesium ions present in my reactive aggregates like dolomites to form MEOH whole twice, MgOH whole twice, which can be expansive in nature and which can cause cracking in concrete. So this is known as alkali carbonate reaction. Okay, so dolomite is like MgCO3. Okay, so dolomite is like ore having a magnesium and carbonate. Okay, so that's why it is known as alkali carbonate reaction because my aggregates are rich in dolomite or carbonate phases. Okay, now how to prevent alkali aggregate reaction? Best thing is to use non-reactive aggregates, or if there is reactive alkylates, there should be low alkali content in the cement or SCM so that this initial silanol group or silanol group breakdown can't happen. And third thing is preventing water permeation by applying suitable coating on the surface. So we have seen here also water also plays a key role here in the reaction. So if we will make concrete impermeable, then also we can delay the alkali silica reaction or reduce the risk of alkali silica or alkali aggregate reaction. Now, the final part in the chemical degradation is freeze and thaw reaction, or what was covered in NPTEL session in the in the heading frost action. So, what are the critical points here in freeze and thaw action is that water expands by 9 to 10% upon freezing. So, it can occupy more volume than ice occupy more volume than water. Okay, liquid water. Now the freezing point in small pores is depressed due to large extent. So if we have a very small pore, the freezing point of water in those small pores will be comparatively low as it is in the large pore. And if the concrete remains frozen throughout its lifetime, then it is not a concern. The deterioration only happens when there is cyclic freezing and thawing action. So it is not just freezing of concrete which will cause degradation. It is the freezing thawing of freezing and thawing effect that causes degradation in concrete. Now, how this occurs? Okay, so initially there is freezing of water which starts in the capillary pores. So we have seen in capillary pores the freezing point of my water will be higher compared to in micropores. So freezing of water will start in the capillary pore. Now the unfrozen water, due to this freezing, it experiences hydraulic pressure by the expansion of ice. So you can see here, suppose there is some ice formation, it will try to expand. Now due to this expansion, this unfrozen water, it will start to experience some pressure on it. And as it experiences pressure, the water will try to flow. Okay, and it will try to flow as, and since the water is like on the pore spaces around cement paste, so this movement of water will generate internal stresses on the paste. Okay, so longer is the flow path of my water, higher is the pressure that is generated by the water. And if this pressure that is generated by the water, it exceeds the cement strength, it can lead to failure in concrete. So this is the effect of freeze and thaw. Okay, that is the movement of water which is generating stresses inside the concrete. Now, in the first image, you can see how this frost action or freeze and thaw action can cause the rock to crack. So initially, water is collected in a tiny crack inside rock. Now, at lower temperature, water freezes. Okay, and it expands. So as it will expand, it will try to crack the rock. Now, when it unfreezes, what will happen? Ice will melt, and due to this, water will be able to grow to a deeper depth inside this rock. And then again, if freezing happens, what will happen? Ice will again form, and that will generate expansive stresses inside the rock, and cracking will further continue inside the rock. And this cycle of freezing and thawing will be repeated until there is complete breakage of rock that will appear like this. Okay. In the second image shows pavement settlement due to frost action. So initially, there is water over the pavement, which is in the form of ice. Now, as ice melts, in the warm condition, this water will start to grow through cracks inside the pavement. Now, as the temperature will drop, the water will again freeze, and it will cause cracking on the surface because ice is occupying more volume, and this repetitive action will cause degradation of the pavement, which can cause heavy damage to the use functionality of the concrete. Now, how can this frost action can be prevented? So by using air entraining agents. So what happens if we have air entraining agents, that will create some additional voids inside the concrete, and this void will help to release the pressure that was generated due to water flow. So suppose my water is moving, now this water will have a empty space where it can rest. Okay, and this space will release the pressure, the internal stresses that were generated inside the concrete. So that's why air entraining agent can help to reduce that pressure that was generated inside the concrete due to water movement, and can reduce the risk of freeze and thaw action. And lower W by C ratio. So if I have a lower W by C ratio, there will be very small pores inside concrete. So the average pore size of concrete will be reduced. And if the pore size of concrete will be reduced, the freezing will become difficult. And if freezing has become difficult, so freezing and thawing effect will be nullified. Okay, so in these two way we can delay the freeze and thaw action. Now try to answer these questions based on the understanding of sulfate attack, acid attack, alkali aggregate reaction, and freeze thaw reaction. In the meantime, if anyone has any doubt, they can ask regarding these four topics. Yes, it can occur, but like generally it occurs in larger pores first, and then it moves to smaller pores. See, gel pores are something which are inside my cement hydrate phases. Okay, freezing will occur only in the free water that is present in the concrete. Okay, gel pores are present in between my CSH layer. So you have seen in CSH there is absorbed water and gel water. Gel water is present in between CSH layer. So for freezing that water, it will require very low very negative temperature, because those what gel pores are very small in size compared to capillary pores. So practically freezing gel pores won't be possible. It is the capillary pores which are generally causing freeze and thaw effect in concrete. Okay. Any other doubt regarding these four topics regarding chemical degradation? If no doubts, try to answer these three questions. So I will mute myself for like a minute. Try to answer all the three questions. Like, try to guess the answers. What can be the correct answer? Okay, I'm muting myself. We have discussed earlier, right? Different types of porosities in concrete: gel pores, gel water, capillary water, adsorbed water. So gel pores, they can form when like there is drying of concrete, and excessive drying can lead to loss of water, gel water also, which can lead to formation of gel pores inside concrete. Or during continuous hydration, the water is consumed. During that stage also, the pores that were filled with water, they will become empty, and the space that was filled with water, it will become empty, and it will appear at as pores. So that is how capillary pores and all are formed. Okay, let us see the answers. Okay, for question number 4, the answer is appearing as C. Okay, so what is the question? What is the primary mechanism of by which acid attack degrades concrete? Okay, so the correct answer will be B. Okay, so acid attack, we are talking about acid attack. So acid attack is not causing any effect on the aggregates. Okay, for aggregates there is alkali aggregate reaction. So acid attack, what it causes? The acid is reacting with the calcium compounds like CH and CSH, and they are degrading, degrading the calcium compounds, and due to that, my strength of concrete is getting affected. Okay, so that is acid attack, dissolution of my calcium compounds. Okay, so acid reacts with calcium hydroxide and CSH, and this reduces the concrete strength and the integrity of concrete. So it is not reduction in capillary porosity which by which acid attack is happening. If there is acid attack, there will be cracking in concrete, and if there is cracking, there will be increase in porosity in concrete. Okay, due to cracking. So the primary mechanism of action is the dissolution only. Question number 5. What will be the answer? Which environmental condition accelerates both external and internal sulfate attack? Okay, so for 5 the correct answer is B. Okay, alternate wetting and drying. So what happens in during wetting, the sulfate ions from the surrounding, they will ingress through the pores and they will form those ettringite formation can happen, which can lead to cracking. And similarly drying will release the pressure, then again pressure will be exerted, so it is like what we have talked earlier, the fatigue effect will occur due to alternate wetting drying in sulfate rich water. Okay, which will accelerate the both external and internal sulfate attack. Okay, question number 6. Which type of aggregate is most susceptible for alkali carbonate reaction? Okay, so for question number 6, the answer is C. See, quartz has inert silica, it is not reactive silica. Okay, so that won't, we need reactive medium. Okay, and we are talking about alkali carbonate reaction, so we don't need reactive silica, we need reactive carbonate phases, and that is present in dolomite. Okay, so if I have a limestone which has high dolomite content, which is reactive, which has reactive carbonates, then it will make my aggregate susceptible for alkali carbonate reaction. Quartz is rich in silica, and that too inert silica, so that doesn't cause any alkali aggregate reaction. Okay, it is the dolomite which has high amorphous content, which can lead to alkali carbonate reaction. Okay, now try to answer these two questions again. More these two more questions. Which of the following strategies reduces the risk of alkali silica reaction in concrete? So I can reduce alkali silica reaction risk in concrete. So the answer is very clear. Like, we have seen how alkali silica reaction occurs. So there is only one correct option which one can easily spot. Okay, yes, the correct answer is C. Okay, so if I have, I'm using highly reactive aggregates, that will increase the risk of alkali silica reaction. If I will increase the alkali content in its cement, then again risk of alkali silica reaction will increase. However, if I am using low alkali cement and pozzolanic materials, then it will reduce the risk of alkali silica reaction. Okay, and if I am keeping concrete saturated with moisture, so moisture is a key agent, because moisture absorption is what is happening in swelling when alkali silica gel is forming, and it will swell in the presence of moisture. So moisture is also not needed. I need low alkali cement and pozzolanic material. So pozzolanic material will consume CH, it will reduce the alkalinity of my cement, and it will also densify the pore spaces in concrete, which will reduce the moisture presence in concrete. Okay, so it will reduce the risk of alkali silica reaction in concrete. Question number 8. Which of the following property improve the freeze thaw durability of concrete? Okay, so again the answer is very simple here. Dense microstructure with air entry in voids. So we have seen earlier, when there is ice formation, there is a pressure that is created due to movement of water. So if I will have air entry in voids, or artificially induced voids, okay, intentionally induced voids inside the concrete, those void spaces will help me to release the pressure that is created due to ice formation, and uh, it will improve the freeze thaw resistance, or the freeze thaw durability of concrete. Okay, okay, so let's move ahead now. And now we'll talk about corrosion in reinforced concrete structure. So this is also like my research area on which I am working. So I'll try to present this more in I will try to discuss this in as simple way as possible. Okay, so most of the concrete degradation, like more than 90% of the issues in practical application, it happens due to the corrosion of embedded steel reinforcement that is present in reinforced concrete. Now, to support this statement, I have shown here few facts of some of the international organization which has related the cost that is incurred due to the damage, repair of damage caused due to corrosion versus the GDP of the country. Okay, so you can see here there are several reports that are generated. Okay, so this is NACE report, impact report in 2014. So NACE is the National Association of Corrosion Engineers. Okay, so according to them, the cost of corrosion repair is estimated to contribute around $2.5 trillion per year, which is about 3.4% of global GDP back in 2013. So 3.4 is a huge number when we talk about contribution of some specific reaction in damage repair of the country. Then this IZADE article that was published in Economic Times in 2021. So IZADE is an International Zinc Association which has written that corrosion damage repair costs further aggregates in India compared to other countries, and it can contribute up to 7% of GDP. So in developing countries like India, it is can go up to 7% of GDP, which is a huge number. And again, ME's the impact report in 2016 said that almost 50% of RC structures which show major repair requirement within the first 10 years of construction is primarily due to corrosion. So whenever we are designing and reinforced concrete, we generally assume it will last for 50 to 100 years. Okay. However, most of these structures, they demand for repair requirement within the initial 10 years only, and all more than 50% of those structures which is demanding for early repair requirements, it's due to corrosion of the embedded reinforcement. So this is how much corrosion is, how much important it is to talk about corrosion and understand corrosion in a concrete system. Now that we know that corrosion is a highly sensitive topic for reinforced concrete, but what is corrosion? So I will like to present you the most simplest of explanation of corrosion. The definition of corrosion here I have broken down into 3 points, and understanding each of these 3 points is enough to understand corrosion. Okay, so corrosion is a natural phenomena of interaction of metal with its surrounding, which leads to loss of functionality of steel and subsequent structural collapse. Okay, so these 3 points is what defines corrosion of a metal, which in our case is steel. Okay, now the first point here, corrosion is a natural phenomena. It is related to the thermodynamics, okay, of corrosion. Okay, thermodynamics, it defines the possibility of something to occur or not. Okay, so this is related to thermodynamics. Okay, corrosion is a natural phenomena that is bound to occur. The second point, interaction of metal with the surrounding, it defines the kinetics. Okay, and these two define the cause of corrosion, why corrosion is occurring. So thermodynamics and kinetics, understanding both will allow us to understand why corrosion occurs. And what is the effect of corrosion? It is the loss in functionality of steel and structural collapse. That is the end effect of corrosion that we'll see. Okay. So, if we see the first point, that is thermodynamics of corrosion, what thermodynamics says, so every metal is stable in its lowest energy state. So, this is a universal law of nature. Every material is stable in its lowest energy state. Now, when steel is made, so these reinforced steel, it is made from iron ores, which is hematite or magnetite. They are processed in industry, okay, in furnaces to make steel. So when we are processing, we are imparting some energy to the system, so we are increasing the energy level of the system. Now my steel is at a higher energy level, so then the natural ore. So natural ore is here and my steel is at a higher energy level. So since thermodynamics says that every material will be stable in its lowest energy state, so what will happen? The steel will start try to convert back to its ore state, and which has a lower energy level. So that's why this process of conversion of steel into its ore state is that makes corrosion a natural phenomena, and that's why we see corrosion will occur. We can't prevent corrosion from occurring because it is a natural process. Now, the question is at what rate the corrosion is occurring, and that is defined by the kinetics. So, simply saying corrosion is not just one reaction, but it is a electrochemical reaction which is made of two parts, oxidation and reduction. Okay, so you can see oxidation is the conversion of this Fe to Fe plus 2 state. Okay, so my iron is converting into iron plus 2 state, that is known as oxidation of steel, and reduction is the conversion of oxygen in the presence of water into hydroxide ions. So this is reduction reaction. So only when these two reactions occur simultaneously, then only corrosion will happen. It is not just one reaction out of these. So this is the interaction of these two reaction that leads to corrosion. So this Fe2 plus that is formed on oxidation, and OH minus which is formed on reduction, they react to form FeOH whole twice, which is what is known as rust or the orange deposit we generally see on the reinforcement. Okay, so you can visualize this reaction from this figure also. So I have the steel rebar. Okay, on the steel rebar, my iron is converting into Fe2 plus, and oxygen, it will consume the electrons that are released by this reaction to form OH minus. Fe2 plus and OH minus, they will react to form FeOH whole twice, which will appear as brown colored product over the steel reinforcement. Now this final product, it can change depending on the amount of oxygen and moisture present, but for simplicity I have just written FeOH whole twice right now. So you can see when this iron is lost, my steel is getting degraded, and this is known as corrosion. Okay, so interaction of metal with its environment. Now, when we talk about reinforced concrete structure, the pore solution in concrete is rich in alkali ions like NaOH, KOH, and calcium hydroxide. Okay, which makes the pH of concrete highly alkaline. Okay, so because of these alkali ions, the pH of concrete inside pH of the solution inside the concrete is highly alkaline in nature. That is like above 12 or 13. Okay, and now in this high pH, what happens? There is a protective layer which is formed over the reinforcement. Okay, so when I have this reinforced concrete structure, suppose this is my concrete and this is my reinforcement inside, due to high pH, what happens? There is one protective layer which is formed over the reinforcement, and this protective layer is known as passivation of steel. Okay, due to this passivation, what happens? My steel will corrode at a very slow rate. Okay, then it would have corroded if there is no passive layer. Okay, but what happens over time, aggressive ions can penetrate through concrete and they can degrade this passive layer, and once this passive layer is degraded, my steel will be directly in contact with the oxygen or other aggressive ions, and it will increase the rate at which the corrosion was happening. And what are these aggressive ions which are responsible for causing depassivation? These are carbonation and chloride ions. Okay, so these are the excessive ions which is responsible for causing depassivation and increasing the risk of corrosion. So suppose if there is no aggressive ions, then this system, reinforced concrete system, will have a very good lifetime. Maybe over 100 years also it can have. However, if aggressive ions can go through concrete and break this passive layer which is formed over the steel, my service life can reduce from 100 years to maybe 10 years also, based on the rate at which the corrosion is occurring, the rate at which these two reactions are occurring. So rate of the occurrence of these two reactions will define the rate of corrosion. Okay, now what is the end result due to this? It is the formation of corrosion products like FeOH whole twice, or maybe other products can also form depending upon the ability of oxygen and hydrogen. And the rust that is formed, on an average, they occupy 4 to 6 times more volume than the original steel. So same as what we have discussed in the chemical degradation, if there is some expansive stresses that is generated inside the concrete, it can lead to cracking in concrete. So that same concept is applied here. The expansive stresses here is generated due to the rust that is formed upon corrosion, and they lead to cracking in concrete in the form of spalling of cover or delamination of steel concrete bond. Okay. So you can see here in the images different ways in which corrosion damage has occurred has been shown. So here you can see the corroded stirrups, they are getting exposed. The main stirrup, there's falling of cover concrete due to corrosion, and there's delamination of steel corrosion interface at high degradation level. Here you can see a bridge pier which is heavily corroded. So there was concrete cover over the top of reinforcement, but due to rusting, the whole concrete surface has collapsed, and my steel is directly exposed to oxygen now, which will corrode at a very fast rate. Here again, you can see a wall which is getting which has got severely corroded, and the spalling that has occurred over the surface of the wall. Okay, and here also you can see a steel structure. Okay, this is a steel structure, not even a reinforced concrete, which has shown heavy damage due to corrosion. So these brown spots that you can see, it is due to rust formation, which has degraded the functionality of the steel. Okay, so this is how corrosion can affect the reinforced concrete. And when we look at this damage on a time scale, so initially until corrosion will start, which is dependent upon the concrete, how slow it will make those aggressive ions to move through concrete, that is stage 1. Okay, so here you can see stage 1. Okay, so this stage is the depassivation time. So I have a concrete cover over the reinforcement. Okay, now my ions are moving through concrete. Depending upon my concrete quality, it will decide the rate at which the ions are moving. So looks more denser is my concrete, slower will be the rate at which the ions will be moving through concrete, and it will delay the time in which by which the ions will reach the reinforcement or the passive layer. Okay, so this is known as stage 1, the movement of ion, or the depassivation time, the time it will take for the passive layer to degrade. Now, once my passive layer has degraded, what will happen? I will reach the stage 2 where corrosion has started, and now this stage is known as propagation period, where the corrosion starts to damage the concrete. Okay, once corrosion has started, rust formation will start, so cracking in concrete will start. And when cracking happens, there is a shoot in corrosion rate. Okay, because now I have a clear path with which ions can directly interact with the steel, because there is a crack through which oxygen can directly reach the steel. And in this stage, the rate at which the degradation is happening will also increase, and that will represent the third stage, which is known as the acceleration period, which has a very fast rate of degradation. So in the first figure, you can see how concrete behaves in these different stages. So initially, before depassivation, I have concrete like this. Once depassivation occurs, cracking will start. This cracking will grow till the surface. Once it grows till the surface, it will provide a direct path for oxygen and moisture to interact with the steel. And slowly, the corrosion will accelerate, and finally, the spalling or delamination of the cover concrete will happen. Okay, so if we will delay the repair of corroded sample, the cost of repair will also increase subsequently. So you can see initially, if we will repair the concrete against corrosion, the cost will be low. However, after spalling or delamination, the cost will be much higher compared to initial. Okay, so that's why corrosion is a very time sensitive process, and the early we detect it, the better it will be to take care of it. Okay, so that was all about definition of corrosion, why corrosion is important, how corrosion occurs, and what is the effect of corrosion. Now, degradation of steel reinforcement in concrete due to corrosion happens due to two reasons. There is direct effect and there is indirect effect. So when steel itself gets affected because of ingress of aggressive ions, it is known as direct effect. So direct effect means the ions which are moving through concrete, they are not causing any disturbance to concrete. They are causing disturbance directly to the steel, and this happens due to chloride corrosion. So chloride ions, they are not interacting with the concrete, they are interacting with the steel after moving through concrete. So that is direct effect. So what chloride do? They cause depassivation of the passive film. Okay, because of chloride ions, and as the passive film will break, my corrosion will be accelerated. Okay, An indirect effect is when concrete is affected because of aggressive ions, which causes depassivation of steel. So in indirect effect, what is happening? The ions which are moving through concrete, they are not causing any disturbance on steel, but they are causing disturbance on concrete, and that disturbance in concrete is affecting the steel. Okay, and this occurs due to carbonation corrosion. So what happens? CO2 from atmosphere, it reacts with the alkalis present in the concrete to form CaCO3. Okay, so as CH is getting converted into CaCO3, as CH is consumed, the pH of concrete will reduce. And since we have read earlier that passivation of steel is due to the high pH environment in concrete, if pH will reduce, the passive layer will break, and if passive layer will break, the corrosion will shoot. So that is known as carbonation corrosion. Carbonation is affecting the concrete, not the steel, while chloride is affecting the steel, not the concrete. Okay. Now try to answer these three questions like based on the basic discussion that we had about corrosion. And in the meantime, if anyone has any doubt regarding corrosion discussion that we have right now, they can ask freely. Any doubts in this initial part of corrosion? What is the importance of corrosion? Why, how corrosion occurs, thermodynamics, kinetics? Okay, sir, please repeat the indirect method one. Okay, so see, we will talk in deep about indirect method. Don't worry right now, but just try to understand what I have said here. We talked earlier in this slide that there is a passive layer that is formed over the steel reinforcement. Okay, as you can see here in this image also, this brown color thing that you can see. Okay, this is suppose passive layer over the steel. Now what will happen? This passive layer, it will cause a barrier for oxygen to interact with the steel. Okay. Now, if there is barrier for oxygen to interact with the seal, where we saw here, oxygen is something which is also contributing to corrosion. So it is like both of these reactions should occur for corrosion to occur. If only one reaction is occurring, it is not enough. Both reactions simultaneously should occur or should occur together to cause corrosion. Now, this barrier, what will it will do? It will won't allow oxygen to interact with the steel, so it will slow down the rate of corrosion. Okay, and that happens due to high pH environment in concrete. So at high pH environment, there is a passive layer which is formed. Now it is not like this passive layer can't be broken. Aggressive ions, when they move through concrete, they can break this passive layer. And what are those aggressive ions? Those aggressive ions are CO2 and chloride ions. Okay, now how they affect the corrosion? So CO2, it affects the concrete. So CO2, it is not reacting with steel. Okay, it is not reacting with steel, but what it is doing? It is consuming the lime, CH inside the concrete, and as CH is consumed, the pH of concrete decreases. So if the pH of concrete will decrease, this passive layer, which we said it is stable in high pH condition, it will become unstable. And if it will become unstable, what will happen? Oxygen will be able to directly interact with the steel and it will increase the corrosion. So that is why we are saying indirect effect. It is not directly attacking the steel, but it is attacking the concrete which is affecting the steel. So that's why indirect. And indirect, it is chloride ions. So chloride ions, they are not causing any effect on the concrete. So chloride in concrete, it is no issue. If we have no reinforcement inside concrete, chlorides won't be an issue. But what happens when this chloride ions, they reach this part near the steel reinforcement? Okay, so what happens? These chloride ions, they interact with the passive layer. They destabilize the passive layer because chloride ions are highly electronegative in nature. So they destabilize the passive layer, they break the passive layer, and then they interact with the steel to form Fe, ferrous chloride complexes and other forms, which can react with oxygen to form rust. Okay, so that's why we said it is a direct effect. It is directly affecting the steel, not the concrete. Now it is clear. Passive layer is like oxidation of steel, initial oxidation of steel that is happening, which is preventing further oxidation to happen. Okay, so Fe2 plus state, it converts into Fe3 plus state upon passivation, and that Fe3 plus state is stable in alkaline medium. So that passive layer, it is just an oxidation of steel that is happening over the top. and it is forming a barrier over the steel. Okay, this is like a very complex thing. It I can't just explain you from word. Okay, passivation is not very much clearly understood till now. There are a lot of theories about passivation, but for now you can remember it is just oxidation of steel. If you want to go deep, we need to take more specific corrosion related course, or maybe at the end of this session I can clarify more when if we have left with free time. Okay, but for now remember it is just an oxidized layer that is formed over the steel reinforcement. Alkaline solution, it is just making that oxidized layer stable. Okay, so that's why we say in alkaline medium passivation happens, because that layer is formed and it is stable there. Try to answer these three questions quickly. What is the primary role of high pH environment in concrete regarding steel reinforcement corrosion? So we have just seen this thing. Okay, so primary role is to passivate the steel structure, forming a protective oxide layer. Okay, so here you can see oxide layer that is formed due to passivation. So it is the ferric oxide layer which is formed. Okay, which electrochemical reaction occurs at the anode during steel reinforcement corrosion? Okay, so we saw there are two reaction, oxidation and reduction. So at anode, oxidation occurs, and at cathode, reduction occurs. So what is the oxidation reaction in these equations that I have shown in the option? Okay, anyone else will try to answer question number 10? Okay, for 10, the correct answer is C. So there are two reactions, oxidation and reduction. So iron is oxidizing, that is anode. So we have seen in natural condition, iron is present in the form of ore. And in ore, we have iron in +2 state and +3 state. So that's why the steel in which iron is at a higher energy level, it will try to convert to its ore state, that is oxidized state. So that's why iron is oxidizing in corrosion, and reduction is happening of this O2. So what this oxidant do? This electrons that are released upon oxidation of iron, it consumes those electrons and form hydroxide ions. And these hydroxide ions, they react with this ferrous ion to form rust. Okay, so this is anode and this is cathode. Okay, so anodic reaction and cathodic reaction, two reactions are happening on the steel surface. For question number 11, corrosion induced cracking in reinforced concrete typically follows what kind of cracking behavior we see upon corrosion? Okay, so this you may not be able to answer because I have not taught here. So due to corrosion, there is longitudinal crack along the reinforcement. Okay, so that is how we can detect corrosion. So whenever corrosion happens, you will see longitudinal cracking along the length of the reinforcement. Okay, that will happen. Okay, so if I can show you here. No, here they have all shown deep spalling. Okay, if I would have, you can see here, okay, in this diagram. This is like a longitudinal crack that was formed due to corrosion, okay, and which led to delamination of cover concrete. Okay, so generally due to corrosion, there is longitudinal crack along the length of the reinforcement, and that is the representation of corrosion induced cracking. Okay. Now let's talk about that carbonation and chloride induced corrosion quickly. Okay. So first we are talking about indirect corrosion. Okay, that is carbonation induced corrosion. Okay. So what happens? Already we have talked a little on this, but I will try to move quickly. So what happens in this? CO2 diffuses through into the pores of concrete and react with calcium hydroxide. As a result, alkalinity of concrete is reduced, and this process is known as carbonation. So I will CO2. Okay, it is reacting with CH. Okay, inside concrete and forming CaCO3. Okay, now as CH is consumed, what will happen? pH of concrete will decrease, and if pH of concrete will decrease, the passive layer will become destabilized. If passive layer will destabilize, what will happen? Oxygen can freely interact with the steel, and if oxygen interacts with the steel, what will happen? The rust will form. What if rust will form? What will happen? Cracking will happen inside the concrete. So this is carbonation induced corrosion. Now this is not a single step reaction that happens. Okay, it is a multi-step reaction. So what happens? First, CO2, it reacts with water to form H2CO3. Okay, and then this H2CO3 reacts with CH to form CaCO3 plus H2. Okay, now CaCO3 is forming. Okay, so calcium carbonate can fill up the pores inside concrete, which will reduce the permeability. So CH was a waste product for me inside concrete. However, CaCO3 is a precipitate. So suppose inside the pore some precipitation has happened. So what will happen? Pore will fill up. And if the pore face will fill up, it will reduce the permeability of the concrete. Okay. However, the associated drop in the pore solution alkalinity from the pH value of over 12 to as low as 8, they disrupt the passivation layer surrounding the steel reinforcement, which causes the corrosion. So that we have already understood here. Though there is calcium carbonate formation, which is reducing the porosity, but this drop in pH is more severe to us because it leads to corrosion effect. Okay. Now, in case of carbonation, what happens? There is a uniform reduction in pH. Okay, so there is uniform corrosion over the steel reinforcement. Okay, so there are different types of corrosion: localized corrosion and uniform corrosion. That is out of scope of this course, so I am not touching that much right now. So just remember, there are two types of corrosion: localized and uniform. So uniform corrosion is something that is happening throughout the surface of steel, and localized corrosion happening which is happening just at some particular location. Okay, so in case of carbonation induced corrosion, there is always uniform corrosion that we see. Okay, and in uniform corrosion, what happens? We can see the cracks on the surface of concrete much earlier than expected. So whenever there is uniform corrosion, the pressure, the stresses that are generated due to corrosion products, that they show their effect on the surface much earlier. Okay, only at the initial stages of corrosion. Okay, so you can see here in the last point I have written, electrochemical reaction happens over the entire exposed surface or over a large area in case of uniform corrosion. And carbonation corrosion can be detected at very early stages because crack will visibly appear on the surface at the initial stages of corrosion. But cracking in concrete, we have talked a lot earlier also. It can be due to n number of reasons. How to know whether it is due to carbonation corrosion, or if not cracking, how we can know up to how much extent this carbonation has happened in concrete? So for this, we use phenolphthalein indicator. Okay, so what we do? This indicator, what happens? It can turn into violet color if the pH is more than 10. Okay, so suppose I have a concrete sample. I have broken that concrete sample from the from the middle, and I have sprayed phenolphthalein indicator over the entire area. Okay, so you can see there is a central patch over which there is violet color. So this patch represents the area which has pH more than 10, and this patch, the colorless patch, represents the area where pH is less than 10. So you can say this is the carbonation depth of my concrete. Okay, and here also you can see this will be my carbonation depth. So up till this depth, carbonation has shown its effect, and here there is no carbonation yet. Okay, now naturally this process of carbonation, it is very slow. Okay, it can take more than 60 to 50 to 60 years for my concrete to get carbonated to such depths like you have seen here. Oh, okay, so in laboratory to study carbonation, we use accelerated carbonation chamber where certain conditions are maintained to accelerate the carbonation of concrete, so that we can study what is the effect of my concrete property in resisting the CO2 ingress. Okay. Now, what are these conditions? We can understand from the carbonation depth modeling. If we will model the carbonation, we'll understand what is the effect of different parameters on the carbonation rate. Okay. So if the rate of carbonation, it decreases over time. Why? Because CO2 is must diffuse through the concrete pores where which is already carbonated. So we have seen upon carbonation CaCO3 is formed. Once CaCO3 will form, it will fill up the pore. Now if the pore is filled up, my CO2 won't be able to move through the pore. So over time the rate of carbonation it decreases, and this rate at which the carbonation, the CO2 is moving through concrete, it is represented generally by this equation. So D is equal to K under root of T. So D here is the depth of carbonation, K is the carbonation coefficient, and T is the time. So it follows such exponential relation. Okay, so over time it will slow down. The depth of carbonation will, the rate at which the carbonation is moving through concrete, CO2 is moving through concrete, it will slow down. Now this K, carbonation coefficient, it is dependent upon different parameters like diffusion coefficient of CO2, the CO2 concentration at the surface, and the amount of alkaline compound that are present inside the concrete. So if the content is less in concrete, then CO2 reaction will concrete will be lower, so CO2 will be able to freely move through concrete. Okay, if there is more CO2 on the surface, then there will be larger rate of movement of CO2 through concrete, and these two processes will affect the diffusion coefficient of CO2 through concrete. Okay, now this K factor is affected by a lot of parameters. Okay, in the figure here we can see one of those parameter, which is relative humidity. Okay, so we have seen here initially in the reaction water is required during carbonation. Okay, so that's why relative humidity comes into play. So the interval of relative humidity which is most critical for carbonation is 60 to 70%. Why is that so? So if you remember the carbonation equation we saw, water is very essential part of that reaction, so that initially CO2 can react with water to form carbonic acid, and that carbonic acid can react with CH to form CaCO3. So if I have very low RH, like below 40%, there won't be enough moisture that will be available for CO2 to react. Okay, and at the same time, if I have very high RH, like more than 80% or 90%, what will happen? My all pores inside concrete will be filled up with water. So CO2 being a gas won't be able to penetrate deep inside the concrete, because the diffusion of CO2 in water is very slow compared to diffusion of CO2 in air. So that's why there is a range in which carbonation rate is enhanced, and that is 60 to 70%. So there is enough moisture and there is enough pores, air pores, that is inside concrete. Okay. Now, other factor that can affect carbonation rate is wetting and drying cycle and the mineral admixture addition. So, in the first figure, we can see wetting drying effect. Okay, so more frequent is the wetting drying, lower is the rate of carbonation. So, you can see if I am doing wetting drying once a week, then the rate of carbonation will be very low. And if I am doing no wetting, then the rate of carbonation will be very high. Why? Because in a saturated concrete there won't be any penetration of CO2, while in dry concrete CO2 will be able to move. So more number of times I'm saturating the concrete, lower will be the rate at which CO2 is moving through concrete. That's why in once a week the carbonation depth is low, while when there is no wetting the carbonation depth is high. Okay, in the second figure you can see the effect of SCM. Okay, so generally this SCM, supplementary cementitious material, they have dual effect on carbonation. Why? The positive effect is they are densifying the pores. Okay, if the pores are densified, the CO2 will find difficult to move through the concrete. However, the negative effect is SCMs is consuming CH to form CSH. Okay. Now, as CH is consumed, okay, CO2 won't have enough CH to react. So if there is no CH available to react, CO2 will be able to freely move through the concrete and it can reach a greater depth. Okay. So that's why you can see here in the figure, compared to Portland cement, the carbonation depth in SCM added cement is generally more at initial ages of curing. However, when I talk about densified concrete where the pore structure has taken control, there won't be much difference between SCM added concrete and OPC based concrete because now porosity is very low. So although there is less CH present in SCM, but since the porosity is very low, the CO2 won't be even able to penetrate. So that will counterbalance both positive and negative effect due to SCM. Now, what can be done to protect against carbonation? So, since presence of both moisture and air is necessary, so which water saturated concrete will exhibit very low carbonation rate. Okay, so we have understood that from initial discussion regarding RH. Okay. Second thing, making concrete denser will reduce the carbonation sheet like impervious surface concrete or low water to cement ratio that we have also understood here when we talked about SCMs. And finally, since the pH drop at the reinforcement initiates the corrosion, a higher cover depth will also improve the protection against carbonation. So suppose my steel reinforcement is here and this is my cover. Okay, 40 mm cover. So instead of 40 mm cover, if I will keep 75 mm cover, then CO2 will need to penetrate to a greater depth for causing the pH of the concrete near the surrounding of steel to depassivate. Okay, so higher cover trap will delay the depassivation of steel. So that's why here it is written a higher cover trap can also improve the protection against carbonation. Okay. Now try to answer these three questions based on carbonation, and in the meantime, if you have any doubts, you can ask. pH we measure. This is the estimation of pH. Generally, we can't quantify pH. Why? Because it is very difficult to quantify the pH of a solid system. If there is saturated concrete, then yes, we can quantify. If there is water inside a pore and if we can dip a pH meter, then we can know the pH of concrete. But generally, when we are talking about carbonation, we just need to know whether the pH is alkaline or it has become acidic, or like it is highly alkaline or low near below 10. So if pH falls below 10, then we can say passive layer will destabilize in this region. And if it pH is more than 10, then we can say that my concrete is alkaline enough to keep the passive layer stable. So that's why we use a phenolphthalein indicator instead of any direct quantification of pH. We generally do qualitative estimation of pH, not quantitative estimation, because we just care about whether passive layer is stable or not. Okay, try to answer these three questions quickly. So, what will be the answer of first question? What is the typical critical pH threshold at which passive layer of the steel reinforcement will become unstable? Okay, so for correct answer for 12th is, okay, so the correct answer for this part is C. So generally, initially the pH in concrete is in this range, 12.5 to 13.5. However, carbonation, it can lower the pH from this high alkaline range to as low as below 9. Okay, and when the pH drops up to this level, like below 10, then passive layer breakdown occurs and the corrosion increases, the corrosion rate increases. Okay, so it is below 10. We can take 9 here. Which environmental condition leads to fastest carbonation rate in reinforced concrete? So that we have seen recently. Quickly, can someone tell me the answer? Question number 13, what will be the answer? Okay, so for 13, the correct answer will be B. at a moderate relative humidity and high exposure CO2, high CO2 exposure. So that will give me enough moisture and enough airspace for CO2 to diffuse and react with the calcium hydroxide. For question number 14, it is kind of a numerical question. A reinforced concrete beam has a cover depth of 40 mm and is exposed to carbonation. The carbonation coefficient is given to us 3 mm per per year, under root year. How many years will it take carbonation to reach the reinforcement initiating corrosion? So how we can calculate the time? Can anyone do the calculation? Can anyone try with the calculation? This is under root year. So when we talk about the equation, the rate at which carbonation occurs, it is D is equal to K under root T. So that's why K is represented at D upon under root T. So D is the unit for distance and under root T is the unit for time. So that's the under root of T. T is the time which is represented in year. Can anyone try this question? How you can solve this question? So you know the equation which governs the rate of carbonation. You know two values are given to you. You just need to put the two values and calculate the time. Okay, so I will just tell you the answer. Okay, so we know what equation governs the carbonation. It is D is equal to K under root of T. Okay, here D is the depth of carbonation. Okay, K is the carbonation coefficient and T is the time it took carbonation to reach that depth D. Now it is given to us that the cover depth is the amount of concrete that is present over the reinforcement. So that is given to us, it is 40 mm. And now we are asked how many years it will take carbonation to reach the reinforcement. So that means the carbonation depth should be 40 mm. So D is 40 and K is given to us, it is 3 mm per under root year. So D is equal to 3 times under root of T. So this T will define the time it will take CO2 to reach the depth of 40 mm at a, if the carbonation coefficient is 3 mm per under root year. So if we will try to solve this equation, how what will come? T will be equal to 40 by 3 whole square. Okay. So if you will solve this, it will come out to be 13.33 square, and this will value will come out to be around 178 years. Okay, so if this is the carbonation coefficient, it will take 178 years to reach the carbonation to a cover depth of 40 mm, which you can see it is quite slow. So this carbonation rate right now, it is very slow when we talk about a natural carbonation condition. Okay, so this is how we can estimate the initiation corrosion initiation in case of carbonation. Okay, so this was all about carbonation corrosion. Now we need to discuss chloride corrosion, but I don't think so there is enough time left in today's session. There is extensive discussion that would I would like to do on chloride corrosion because this is a very important part. So let's do that discussion in the next session. We'll start the next session with the chloride corrosion discussion. Okay, so that I can discuss all these things properly. So we'll first talk about why, how chloride corrosion occurs, what different parameters it affects the chloride corrosion, then how we derive that initiation period using fixed second law, how we estimate that diffusion coefficient in laboratory condition, the testings, and how different concrete grade affect the diffusion coefficient, and how finally we predict the service life. So that all discussion I want to do with you, so that we can do in the next session. So for now we'll conclude the discussion. So today we talked about durability, service life, and repair maintenance of concrete. We discussed about degradation of concrete, first talking about chemical degradation induced by acid attack, sulphate attack, aggregate, alkali aggregate reaction, and freeze thaw attack. We talked about corrosion reinforced concrete, a basic overview, understanding the kinetics and thermodynamics, and then we discussed about carbonation induced corrosion, the mechanism of action, and modeling the rate of carbonation corrosion. Thank you. So if anyone has any doubt regarding the discussion that we have done till now, you can ask. Sir, how T to the power 1 by 2 will come? So this is general equation of carbonation. Okay, the this is like how we represent carbonation depth. So carbonation depth, it is represented as K under root of T. That is a model which, that is a basic equation which models the penetration of CO2 through concrete. Okay, so that is a very basic general equation that is used. Okay, so this is known, basically known as square root law or something. Okay, so how, like the diffusion of CO2, it follows a square root under root condition. Okay, that's what we say. You need to remember that thing, like this is how it is modeled. Okay, I will stop the recording for this session and then I can take further